All right, so this will be my second take on this kind of cryptography, which is going to be about modular arithmetic, and it's actually straightforward. You'll see in a moment. And somehow this also has to do with Alice and Bob, but even though it looks very colorful, I have to leave this out. All right, so here we go, cryptography. If I scroll down a little bit, that's the Wikipedia page, public key cryptography. And there again is Bob and Alice, but then it also talks about these two researchers, Diffie and Hellman, and then there are three more. Let's see here. They are Rivest, Shamir, and Eilman. This all goes back to the 70s and 80s. And all five of them were cryptographers and mathematicians that worked with this kind of modular arithmetic. So I'm going to go here. And here's actually a very good example, the one with the clock. So here you have 9. And then you add 4 hours. Well, technically, you're going to be at 13 hours, right? But we call it quite often 1 o'clock because our day as it is built on 24 hours, but we have from midnight to noon, we have 12 hours, and then we have, again, 12 hours. So it kind of rolls over. And let's see, when I go down here and I think I click on applications, then this kind of modular arithmetic goes with cryptography, just as it said before. All right, here's one more thing that I want to share. This is basically the same thing. So when you go to 14 hours in the afternoon, well, that's actually 2 o'clock, right? 2 p.m. And basically what you do is you take the 14, you divide by 12, which it says kind of right here, 14 divided by 12, which is 1 point something, but instead you're going to use the remainder. In fact, it says it right here. There we go. 14 over 12 is 1 with a remainder of 2, and this is the way to express it. 14 mod 12 equals 2. So I'm going to do that over here. And so 16 over 3 is 5 point something, but we're not going to look at the... This is actually kind of the reason why I started this over, because A, it's not writing, and B, it smears with my hand here on the screen. All right, so that's 5. If I ever get this done, I'm telling you, in my first take, the same thing happened. This is just 5 point something, where we're not interested in the point something, we're interested in the remainder. So 16 divided by 3 is 5, remainder 1. There we go. And to express that, after I take this off here, to express that would be like this here for modular arithmetic. So 16 mod 3 equals 1 is the same as saying 16 divided by 3. Forget about the 5 that you get, but look at the remainder, 1. So 90 divided by 4 is 4 point something. But again, we're interested in the remainder. So 9 divided by 4 is 4 with a remainder of 3. I'm trying really hard to do this. And so the same thing happens here. And notice, ooh, interesting, I made a typo there, right? I did say the remainder is indeed 3 after I divide by 4. 35 divided by 7. Ooh, nice. I'm able to write, yay. 35 divided by 7 is 5 with a remainder of 0. So here we go. And 74 divided by 15 is 4 with a remainder of 15. I'm sorry, with a remainder of 14. There we go. Oh, all right. Improved only slightly from what I did before. There it is, 74 mod 15. So again, divide 74 by 15, which is 4, but forget about that. Look at the remainder, which then is the 14 here. So as I said, slightly improved. I did actually type more this time around. So here's the first thing. That's actually really simple. Just divide, look at the remainder. That's actually it, modular arithmetic. All right, have to introduce something else because we're going to get to this RSA encryption here, well, right away. And that actually goes back to these 3 researchers that I mentioned earlier. Here we go. If you look at, where'd they go? Hold on. Here we go. So these 3 here, they're also photos from them. Rivest, Shamir, Edelman. So that's RSE. All right. So in order to get there, we need something else, which are prime numbers. You're familiar with them, numbers that can only be divided by themselves and by 1. So we have 2, 3, 5, 7, 11, 13, and so on. 2 is the only even prime number that exists because all other even numbers, well, will be divided by 2. Hence, it can all that's the only even prime that is possible, right? 3, 5, 7, 11, 13, and so on. And you can see that, well, they're kind of out of step here, so they're not very regular, and there are longer gaps, and the gaps actually get larger and larger. You still get some pairs here, like 13, 17, 29, 31. They actually happen quite often, but there will never be a triple, by the way. So for example, after 29, 31, 33 cannot be a prime number. It's divisible by 3. Same thing happens with 17, 19, 21 is divisible by 3. So triples are not possible because one of those 3 numbers will always be divisible by 3. So pairs work quite a bit, prime numbers, but just pointing out something about prime numbers, okay? So the RSA encryption works with prime numbers, and the larger the prime numbers are, the better. So I chose 2 large prime numbers here. I'm going to show you where I got them from. So this one here is a table of the first 10,000 primes, and I was actually looking the primes up to number 10,000, and that gave me the first 10,000 primes. All right. So for example, 3,457, somewhere in here, I found it. There it is. All right. So it's all good. And you can look for the other one. And in real RSA encryption, they actually go with really, really large numbers. So a moment. Oh, there's my calculator. All right. Because I'm going to show you in just a moment. So I'm going to multiply these two here, 3, 4, 5, 7 times 5441 equals, there we go. And I already wrote this here. As I said in my first take, I messed that up by just handwriting. So 18,809,537. I will show you in a moment that these 2 prime numbers are actually secret in the encryption, and this can be public. The problem is that if a computer tries to decipher that number, it's pretty tough to figure out what the original prime numbers were. And that's one of the reasons why this kind of encryption with the prime numbers is being used. And I get back to the modular arithmetic here very soon. Then the next thing to do is multiply these 2 numbers. And you see the relation between these here. So 3, 4, 5, 6, which is 1 less. So subtract 1. Multiply by 5440. There we go, enter, and that's this result here. This is called a phi-n or Euler-Totient function that, well, will help here in the process or is necessary. I'm not going to get into too much detail. I'm just going to show you this one here. This is actually really kind of like how the way the algorithm works. Okay, remember I chose 2 prime numbers. They're supposed to be really, really huge, and I chose 4-digit ones in the thousands. Not too huge, but when you multiply them, you still get 18 million. If you do the real thing, I think you come up with like way beyond quadrillions or what have you. Okay. Anyway, so I chose yet another one, 8,971. It's also somewhere on here. And then I compute the modular inverse with the help of the coprime. You might be familiar with what an inverse is. For example, 4 has the inverse of 1/4 because 4 times 1/4 is 1. Okay. 15 has the inverse of 1/15. 15 times 1/15 is 1, and so on. So something similar happens here with the modular inverse. The way it actually works, I'm going to calculate this one here. I have several calculators open that determine this one. So here's the inverse modular calculator, and I keep doing that. I should reset this here before I use it again. There we go. There we go. Now I have to figure out which one comes on top. Let's see, 18 million. Oops, 800,640, and then I put in here the 8971. Let's see what we got. There it is, 3,688. So, and this one here, and if you multiply them modular from them in the other way, you come up with 1 again. All right, there's a few more steps here. So let's look at these here. I know I'm throwing a lot of stuff at you, and this is just the algorithm, the way it works. I'm not getting into detail, trying to explain everything here. Just, hey, this is the way it's being done. And I do it actually 3 times over. This is my first one. Then I'm going to go to another example. Then I'm going to go to another example. My last one will actually be my Google Sheet. All right, so here we go. Encrypt something. For example, the number 71, which in the ASCII code is letter G, capital G. So you have a message that you want to get across maybe bank account number or something, and you have all these letters that you need to encrypt. One of them may be a capital G. And so you choose the ASCII code, for example, 71, and then you encrypt it. And here's what you do. You take the 71 to this power that we have up here, 8,971 right there, and mod 18,809,000, that's the number from the previous page where we multiply those two large prime numbers with each other. And then you figure out what that C is. And I'm telling you, this gets out of hand. So actually, I'm not doing this one here. If I decrypt it the other way, so the other person then, or the other side where I'm going to send my secret message to, would have the decryption here. They would do this one. They would actually take whatever this C is here, take it to the 3,688. There, you recognize it, and mod of the same number that was on the previous page. And then they come up with, hey, guess what? 71, which is the original encryption. Okay. As I said, this is getting out of hand. This is just too huge. I don't have a calculator that actually can figure this out. So I'm using a different kind of example. And I'm going to give myself a little break here and pause the recording, which I also had a tough time yesterday when I tried the other one. So see you in a moment. All right, so I just need to take a break here to look at the next section. I said I'm going to do a total of 3 examples here. So I'm almost ready with my third example. Just a little introduction. Basically, what I just showed you here was, so I looked up, I had ChatGPT help me here, define these variables and their meanings, and that, yeah, some of them are secret. So the 2 large prime numbers are secret. I chose 4-digit ones in the thousands, but the real ones, they might actually have 20 digits. It's just incredible how that is encrypted. Then here's the modulus. I calculated earlier, simply multiply the 2, then subtract the 1 from that, which then gives the phi n function. And that, as it says here, that's actually a public key. So that would be available. And then find yet, or use yet another prime number that is actually co-prime to this one here. So the 2 cannot be divided by each other. And then private exponent, here's this inverse modular. And so that's how privates. And then there's the plain text, that was my capital G. And then these are the 2 equations I had toward the end where I said, hey, this was actually getting out of hand. So let's look at an example. And different examples. I have RSA Cryptosystem. Here are the names again. Rivest Jamir Edelman, RSA Cryptosystem. That's apparently one of the systems that messages are encrypted when they go through the internet. Notice it's not that old. Well, for us, maybe these times, 50 years, I was still in elementary school at the time. And I never learned anything of that in the 1980s when I went to school, because it was really new and it wasn't yet quite necessary. But today, of course, it is. So let's see, I'm going to scroll down here. There was something. Oh, yeah, I wanted to look at the example. So here's this example that I'm going to cover, which I pretty much copied here. These are actually the same numbers. So when I look, for example, here, let's see. I need my calculator. There we go. There it is. So when I multiply 61 by 53, there it is, of course, 3,233. Then I subtract 1 from each, 60 times 52. And I come up with 3,120, which is not 780. This is actually where I stumbled yesterday and stopped my first take, because they're like, oh, what the heck happened now? Well, they're using a slightly different way of doing it. If I divide this actually by 4, there's the 780. There is, I called it the Euler-Totient function. This one actually is the Carmichael-Totient function. So it's a slightly different one. And don't ask me why one or the other is being used. I just accept it as such. All right, so I have the 780 here now. Then I choose another prime number. Notice actually the prime numbers are smaller than the last time, right? So they can have a workable example here. Even mine were too large. So 6153. And now I'm going to have 17. And again, I have to find the modular inverse. So I'm going to plug that in here, 17 and 413. Let's go try 17 and 413. I always have to figure out which way to put, no, that's not true. That's not true. 17 and 780. And there's the result, 413. So that's the modular inverse coming from this one here. And if you turn these around to 413 here, and the, let's see, it was the, yeah, actually the 17 here, that would be then the modular inverse, and you get 1 when you take the modulus. All right, just I have to figure out one more little thing here that I have to pause, so I'll be right back. All right, I'm prepped for the last part of this second example. So here now I got my 413, or I have the 17, so I have all these here, these bunch of numbers. And yeah, why not these bunch of numbers? Well, because they have to be all encoded in order to get a secret message across. So it cannot be easy. It has to be complicated enough that it's really tough to decipher if you don't have the right keys, and especially if you don't have the secret ones. So here we go. So this is the way of doing it. And then here would be encrypt something. 65, by the way, in the ASCII code is the capital letter A. There we go. And here's what you do. 65 to the 17 power mod 3233. So 65 to the 17th power, that's a pretty large number. It's 10 to the 20 something. And then you divide it by 3233, and you're only interested in the remainder. So let me try to show you that. I believe that actually works in this calculator. It's not too large here. So 65 to the 17 power. There we go. It actually says here 6.599 times 10 to the 30 in the very end here. So it's a very, very large number. And then now you divide it by the 3,233. And sure enough, the remainder when that is being done is 2,790. And I mean, yeah, try to do that on paper, right? So that's what we have computers for. So there's the 2,790. Okay, so here it's being encrypted, that original capital A, to the number 2,790, and people have no idea what that now means. Now it has to be decrypted on the other side. For example, you're setting a password across, or your digital signature or something, and so it has to be decrypted. It has to come out to a capital A. So you do this. Okay, that would be now with the exact same thing, but 2,790 to the power 413. It actually shows it 1.08 times 10 to times 1,423, which means you have a number with more than 1,400 digits. Okay, and then you do mod 3233. So there it is. And note the remainder is not 0. It's not. Even this calculator cannot do it. So I looked at the algorithm here and the way that modular arithmetic works, and I was actually able to do it in Excel or Google Sheet here, and it's not too hard. There's that 2,790, which is my encrypted message, which I have to decrypt. There's the exponent 413. Here is the what I divide by 3,233, and then there's certain ways of manipulating this one here. So I'm just going to pull this one down and watch. I think it's going to appear somewhere down here what the result is. So when I pull this one down, there we go. All right. Okay. And I pull it down further, and it's not that hard behind it. And there it is, 65. So here is again a very large number. It just doesn't work, but with a trick, I can even make it work in a Google Sheet, and I'm back to the 65. Still, if I did this all on with the Google Sheet for you, then it would be just still too much. So I have to reduce it yet. So my third example will come up after I take another break. Just one little thing here to point out. Let's see, I think it was this one here. So here I asked Chad, why is modular arithmetic considered very safe? And it gives all these things here. So hard problems, large key sizes, one-way function, meaning that you go in one direction, you can encrypt something, but going backward is really, really tough. So the other side of the computer where you send a message to, they have the decryption key. Well, they can do it because they have the decryption key. But if you're trying to guess at it, even with a brute force attack, it's not going to work. And that's what it says here. So it's secure against brute force. It probably says that somewhere here, but it's also secure against frequency analysis, which I didn't quite figure out how it does that, but there are certain things in there that does that and so on. So when you look at modular arithmetic, which basically just means divide two numbers and you're interested in the remainder. That's all that means. You know, a typical, very simple mathematical thing from third grade, okay? But that is apparently at the heart of the cryptography that is being used on the internet these days. All right, as I said, I'm going to take a break here to focus and prepare the last portion here. So my third example. All right, so I think I'm ready to do this last part here. So my third example, and you remember these large prime numbers that I used earlier, okay, 4 digits, which are yet a lot smaller than what's really used in encryption. Then I went over to the example and they used 2-digit prime numbers, so you see 153, right? And now my third example, watch what happens. These are my two prime numbers, 3 and 11. They're certainly not large, but this is what the Google Sheet or Excel can actually handle for this kind of math. And then here is what happens. So 3 times 11 is 33, right? Then you subtract 1 from each, so it's 2 times 10, which is 20. That's the phi n here. Then you choose yet another prime number. Again, a huge prime number, right? There it is, 7. So I use 7 here just because, again, that's the way the Google Sheets can handle that. Then I have to find the inverse modular for that. Actually, the result is already here, but let me show you. I use these two numbers, 20 and 7 here on the next sheet. I've prepared this one here. I plug in a 7 here. There we go. I plug in a 20 here, and there we go. It's calculated, and the inverse is found. When you do that, you get a 1, and the inverse itself is the 3 that I showed you right here. There we go. And if I use this kind of calculator, again, it's the inverse modular calculator. So when I use 7 and 20, I should get 3. There it is. So there they come from. So the 7 here is used to encrypt it. The 3 is used to decrypt it. So here would be my secret message, bank account number, something I kind of mentioned that casually earlier, right? So bank account number 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. There we go. That's it. There's also a colon in here. So that's my secret message. And there are a couple of spaces here as well. There we go. Then this is the ASCII code. I also mentioned that casually. That's what you use basically on your computer in order to encode each letter or each symbol that you have on your computer. So 66 stands for capital B, 97 for lowercase a, and so on, right? And now you encrypt it. And the way it's encrypted here is actually with that formula that you still kind of see over here where I pulled this one up. So you take one number, your ASCII code in this case, to the power 33, I'm sorry, 7 here, and then you divide it by 33 and see what you get. In this case, you get a 0. And then actually Google Sheets or Excel actually balks at that and says, oh, no, I don't want to calculate it. It's too much for me. Some numbers it does calculate here, but some numbers it doesn't, and then it cannot decrypt it either. Okay, so I got other columns here. It's way on the right-hand side, so I'm going to make this larger over here. Hold on. There we go. There we go. So here I used a little trick here. It's not a trick. It's a mathematical thing here that is being used for modular arithmetic. Notice when I go here, I have simply the mod here. So it says take a number, divide by another number, be interested in the remainder. Okay. So notice over here, I do basically the same thing, but I do it twice. So basically what it's doing is take the divide by one number, then be interested in the remainder, and then do it again. Divide again by the same number, and you're interested in the remainder. And now it actually works. It is actually able to compute all these. Notice here, especially these numbers down here, they're all the same. But with this mathematical, again, it's not a trick. It's a mathematical way of doing it. It works just fine. I'm able to actually calculate it in Google Sheets. So here, this is actually the encrypted sequence here. I know this could be actually still resolved for frequency analysis, but there's other things that I didn't pay attention here, that I didn't incorporate, that would actually hide that fact. And it's a short message too, bank account number 123 and so on. It's hard to make a frequency analysis there. So then you go over here and you go to the decryption. So the decryption now is, again, you take the encrypted number to the power, which is the modular inverse, and then divide again by the 33 here. And you do it twice, because that way the Google Sheet is able to handle it. And now you get, this one is the original plain text that you originally put in. And you know what? It actually, there it is, actually. Well, that's what it should be. However, it actually doesn't do it. Notice this one is a 0, but that's a 66 over here. That's a 31. That's a 97. Oh, that didn't quite work. Here's a 32. That's cool. There's a 32. Here's a 17. Hold on. Nope. That's not what I meant. It doesn't work very often, so it doesn't work at all. So, I mean, not very often. There was another one here. This is actually, so this is just copied from the very front. But here is actually what you get. So this one actually is over here. Again, it's the same sequence here. When you look at this one here, this is totally garbled. Okay. That's what we get here. So actually, technically, this one here shouldn't even be here, I believe. Let me see what happens when I take this out. Okay, I can just take that out. All right. Now, what I did here is, remember the number was 33? And I'm supposed to come up with 66 here, but I came up with 0 actually when I do it. Okay, well, if I add 33 twice, I'm back at 66. Notice this one is a 97. I came up with 31. I'm supposed to come up with 97. So I'm adding 33 3 times. Okay, no, 2 times. And I'm back at 97. Here on the 11, I added 3 times. 11 plus 99 is indeed the original 110. So that's my way around in this Google Sheet here to come up with the right message. So even though this one here is still garbled, this one here is multiplied by 1. You can see that up here. This one is multiplied by 2. You can see it up here. This one is multiplied by 3. You can see it up here. And if you look at these here and you kind of go across, you actually will find the message. Bank account. You see the count there? Account. There we go. See the N? Number. There we go. See the colon here? And then 1, 2, 3, and so on, right? So you have to put these 3 here together. That's the way I designed this Google Sheet. All right, I think I'm finally done with this one. I know, very complicated, but it's encryption, and it has to be safer than what I showed you before. All right, I think I'm done.